Hey guys, this is Yanni from Trilion Quality Systems, and in today's tutorial video we will be going over how to do an FEA comparison um, in ARGUS. So today we're going to go over how to compare the FEA or the finite element analysis to the actual measurement panel. For example, here you can do by importing the native data, you can align the ARGUS measurement to the FEA and then compare the actual results to the theoretical FEA results. Some of the prerequisites that you want to be sure to be aware of is that we're going to be using SVIEW. You want to have the correct FEA data with the following, the major strain, the minor strain, and the thickness reduction. And then you also want to have the correct layer of the FEA data for the proper alignment, which means if you're doing the outer layer or shedding water, or if you're going to be doing the inner layer or the lower layer, as the terminology is in FEA groups, for parts that are holding water. The workflow that we're going to be going over is we're going to start the SVIEW file. We're going to import the data or the FEA data. We're going to align the ARGUS to the FEA data. We're going to compute the deviation to CAD, which shows us a nice dimensional difference between the two meshes. We're going to map the FEA data onto the ARGUS mesh data, and then we're going to compare the two results, ARGUS to FEA, to get a full panel comparison for reporting. Okay, so we started the SVIEW software. You'll see here pretty generic. We're going to start with going to File, Open, and as we normally do, we're going to go ahead and navigate through our Windows Explorer to find our ARGUS measurement. In this case, I'm using the GOM Workshop FEA data. This is going to be on the net. You guys can download this anytime you want. But as you notice here, I'm picking the .argus file because it's looking for a strain measurement, hence what SVIEW stands for, it's strain view. From here, I'm just going to call this any generic name I want to. For this one, I'm going to call it FEA test, and I'm going to call it 1. And I'm going to hit OK. It's going to bring in the file just like it normally would, as you've all typically done before with SVIEW. In this case, you're going to see it starts off with the 0 to 0, which is the theoretical flat blank on the screen. We also have the 0 to 1, which is the actual flat blank that you guys probably shot. If you've done it, that's great. And then you're going to typically have your form panel, which is the results that you guys normally go with. So these are the three results, or in this case, the three results that we have. You might just have the form panel and the theoretical blank, and that's fine too. So the next step that we're going to do is we want to import the FEA data that was given to us. We're going to start doing that by going to File at the top of the screen here. We're going to go to Import, and then we're going to go to FEA data. From here, it's asking you where is the data set that you want to import. So we're going to use the white arrow to navigate through our Windows Explorer to find out where that file is that was given to you. In this case, I have an ls-dyna file. It's a native file that came from that software. You guys might be using Autoform or PAMStamp, and you can definitely bring in native files like that. So I'm going to select it, and I'm going to hit Open. From here, I'm just going to hit OK and just bring it in and see how the data looks. So what I notice initially here is that the green side is facing up. And if we look at our ARGUS data set, as we typically see, the green side is facing down. That initially is telling me that this file is backwards. It's inverted in a sense. Our surface normals are different, meaning that our results are on opposite sides of the part. So to rectify this, the quick solution would be to just right-click down here where it says CAD data in the lower left-hand window. We're going to right-click Treasure Hunt, and we're going to delete that element. We're going to hit OK in the next menu, and it's going to get rid of it. So to bring in the correct side of the data, we're just going to repeat the command, and we're going to go to File, Import, FEA data once again. We're going to navigate once again back to that same simulation file that we did before. Within our file structure, we're going to hit Open with one difference is that now we're going to click this little button under where it says Parameter. We're going to invert the normals, and we're going to hit OK. Now you'll notice that when the data comes in, the blue side is facing up. That's exactly what we want to do, as now we know that the surface normals are facing the same direction, and we'll be able to map them, as you're going to learn in a few minutes, on the same side of material so we can make that comparison. So now that we have the data sets in the same project and they're all looking good, we now want to go ahead with the alignment of the two panels and get them in the same part space. And what's about to happen is that we're going to move the ARGUS data to sit in the same position as the simulation data set. So I'm going to go to Project, Registration, and then Manual Pre-registration. The software will then split the screens. You'll see your ARGUS result on top and the FEA dataset or the simulation dataset at the bottom. What it's asking you to do is pick similar points in at least 3 locations for triangulation so it can do a kind of a real quick alignment to get them close. So I'm going to zoom in to both areas. I'm just going to start picking here. I'm going to do a control click on the top one and then a control click on the bottom, and you'll notice that now I have a 0 on both points because it's trying to associate those 2 areas as being the same. So now I'm going to pick a second point here, and I'm going to use the angle of this leg. I like picking surfaces that have different vertices because it kind of locks it into position. So we're going to do a control click on this leg and a control click on this leg right here. And then I'm going to repeat the command on the other leg on the other side here, on the little sidewall as well. Control click here and control click here. So you'll notice here that after I pick the 3 points, if I zoom out here, you'll see the 3 points selected in each of the measurements, and then you'll also see them in the menu that now there's a deviation under each point and there's a transformation deviation, and in this case it's at 2.49 millimeters. That's pretty close. That's great. I like being right around 6 millimeters, no more than that if I can. You can pick more points if you want to. It needs at least 3, but you can pick more if you want to. From here I'm going to hit apply, and when the apply button goes gray and the menu goes empty, that means that the command has been completed. So now I'm going to hit close, and it's going to take me right back into my evaluation mode. You'll notice that the 2 measurements are sitting right on top of each other. They're no longer skewed. Now you can go ahead and say, you know what, I'm pretty close, but now there's one more alignment method that we're going to do to get it even closer. And again, we're going to go back to Project, Registration, Best Fit Registration. So from here, you'll notice that it's automatically picking the FEA dataset, which is great. It's using a search radius of 5 millimeters. I'm keeping my auto adjust search radius on, but it's not letting me do anything because this is a selection dependent function. So you as the operator have full control over the areas that you want to select on the part. If there's any kind of springback on these edges around the outside of the part, I wouldn't pick those areas because it might skew the alignment. I wouldn't only pick the end of the part for the same reason. It might skew the middle of the part that might be sitting well. Adversely, if you're looking at a part that's oil canning quite severely while it's sitting on the table, just have the acknowledgement that you have the full control over picking areas that will lock this part in and be able to compare it nicely across the way. So with that said, I'm going to go ahead and do a right-click treasure hunt in the 3D view, and I'm going to do a select through surface, and I'm just going to draw a box around the middle part of this panel here, and I'm going to use this area to lock this part into it and see how close I get. So now that I've selected this middle part, I'm going to hit preview, and you'll notice at the bottom of the screen the numbers are adjusting accordingly based on how it can shake it all together using the 2 mesh bodies to align it. You'll notice that it gives me a transformation deviation of 0.46 millimeters, and it tells me that it used a search radius of 2.3 millimeters. That's pretty great. I think that's close enough for what we're doing here with the training, so I'm going to hit apply. And once the apply button goes gray again, I can hit close, and the command is now complete. So I can hit a right-click treasure hunt and deselect all, so you can see now that the 2 are within about a 0.5 millimeter of this middle section aligned. I don't know what it's doing out here on the ends, but I think this middle area is pretty much going to stay the same between the 2 parts. It seems pretty rigid. So from here now we can do everything through all the menu selections. You don't need to be looking at the FEA dataset. So you can actually turn it off by clicking this little square toggle here, and visually you're going to be looking at whatever strain semantic you're looking at here at the top. So we're going to do some next steps here. We have to get the FEA data prepared for the comparison, and these are going to be the next steps for that. The first thing that we want to do is we're going to right click on this CAD data or the FEA data, and we're going to go to Edit Properties. Now this step is only done just to make this nice title here a little bit shorter. So instead of calling it the suspension arm simulation, we're going to call it FEA data. And we're going to hit OK. That just shortens up the name, so when you do the comparisons later, you're not looking at a big, long name throughout the comparisons. The next step that we're going to do is we're going to right-click on the FEA data once again. We're going to go to CAD FEA, and we're going to go to Edit FEA Data. For this particular training exercise, we're going to be renaming some of these principal strains because of how they were given to us from the simulation software. You might not have to do this. It might actually be called major strain or might be called minor strain. That's great. But for this, this is just an example of how you can rename them. So in this case, the result of first principal strain, as we know, first principal strain is major strain. So we're going to rename this FEA, and we're going to call it major strain. And then we're going to hit apply. And once we're done with that, we're going to hit this white arrow to see what other strains were given to us within this simulation. In this case, we have two other strains, so we're going to go to second principal strain. And as we know, the second principal strain is minor strain. So we're going to call this FEA minor strain. Now you can keep the names as they were given to you if you want to, but I'm doing this to have easier understanding of what they are, and for the shortness of the name, it just makes it easier and more comprehensible for other users. I'm going to hit apply again, and then I'm going to go right back to the third one. In this case, it's called result of effective strain. In this case, this would be the von Mises strain. So we're going to call this FEA Mises, and we're going to leave it just like that and hit apply. Once this is done, you'll notice that all three strains have been renamed. Again, you might not have to do this, but this is the way you do it if you need to. All three have been done, and you'll notice that the unit here is in logarithmic or true strain, which typically is what comes out of simulation softwares. So now you can hit close. So now that we've prepared the FEA file for comparison, we can now proceed with the other steps of creating the deviation to CAD, mapping the results, and then comparing it. So let's get into it. So we're going to go up to the top here under CAD FEA, and we're going to do a compute deviation to CAD. This is going to be a straight dimensional difference between the two mesh bodies as it compares to the alignment that you've created. So you'll notice that the system automatically picks the reference CAD, which is great, and it's going to automatically give it a name, distance to FEA data. This is going to create another strain semantic up here at the top of your screen here. Your search radius should be 5 millimeters. You should respect the normal vectors, and then the max angle between those normals should be 120. This should stay the same. If it's not, go ahead and change it at this time, and then hit OK. Once you hit the OK button, you'll see that the result on the screen is going to change colors, and the strain semantic at the top here should automatically have been switched to distance to FEA data. Again, when you look at your strain tensor on the right side of your screen here, you'll notice that this is a millimeter unit. So it's a straight dimensional difference between the two data sets. So you can actually pick any point on here and it'll give you an actual dimension of how far the two data sets are apart. What you're trying to see is how close they are. You can see if there's any spring back, how close you were to your alignment in the middle of the part or any other areas, and just really understand, like a quick dimensional check. If you want to do this next to the press on the floor, you can definitely do this. So from here, our next step would be to map the results from the FEA data onto the mesh data set of the current ARGUS measurement. So we want to take those results and we want to map them. So if I'm going to go to CAD FEA map FEA data set, and again, it's going to bring up this nice menu for us, and it's going to automatically pick the reference data, which is the FEA data set, and it's picking the FEA data set of the major strain, the FEA data major strain. So we're just going to go ahead and keep the name the same because it's actually telling you the FEA data, and we're mapping the FEA major strain. That's great. Search radius should be 5 millimeters, respecting the normals, and we're going to keep the max angle between normals at 120. So we're going to hit OK. And you'll notice that now we have the major strain of the FEA data mapped onto the real estate or the mesh data of the current ARGUS measurement. This is important. That's why we're doing the alignment, is to make sure that they're, that the nodes are aligned 1-to-1 right on top of each other. So you'll see here the strain tensor showing a logarithmic value. You'll see the histogram on the right here. And again, we're looking at the major strain of the FEA data. This is not a comparison. This is showing you the results from the simulation file. The last step that we're going to do is compare. So that what I want to do is map all of the strain semantics that you brought in with the simulation. So we will repeat that command. We're going to go to CAD FEA, map FEA dataset, And then this time, instead of doing the FEA major strain, we're going to do the FEA minor strain. And you'll notice the name automatically updates. We're just going to hit OK. And we're going to do it one more time for the MECE strain. So CAD FEA, map FEA, we're going to pick FEA MECES. It updates the name again, and we're going to hit OK once again. So we did that 3 times, and now we have 3 new semantics in here, and they're all the FEA data for each prospective strain that we see, major, minor, and MECES strain. So now we've gotten this far, but we have not done the comparisons yet. So the final step to do for all 3 of these is going to be to compare it. We're going to go to CAD FEA at the top here, and we're going to go to compute deviation for 3D data set. Now, this is important to keep track of how you're doing this because if you go the wrong way, you can tell somebody to fix something the exact opposite way you were intending. In this case, I recommend keeping the current ARGUS measurement results as the basic data set, and then you want to subtract out the simulation to find out where exactly your current part sits in regards to strain. So we're going to keep the basic data set being the major strain. We will subtract out the FEA data major strain. The name at the bottom will automatically update as the difference between the major strain and the FEA major strain. We're going to hit OK. Now notice this error message that pops up here. It's telling us that the basic data set is in technical or percent, which is engineering strain. The data set that's trying to be subtracted is in logarithmic, which is true strain, and they're different, so it doesn't understand how to make that comparison. So we have to hit cancel here and cancel in the next menu as well, and we have to go back and change the current units of our ARGUS measurement that we currently did. So we have to go to the major strain of our current measurement, do a right-click treasure hunt in the 3D view, go to visualization parameters, and change it from technical to logarithm. And you'll notice that updates automatically. We have to repeat this step for any other strain semantic that you'll be comparing. In this case, we're going to be doing the same to the minor strain. We're going to right-click treasure hunt in the 3D view, visualization parameters, and then go to logarithm. And the same thing we're going to do to the MECE strain in this case. I'll turn it on. And then we'll go ahead and pick MECE strain, right-click in the 3D view, visualization parameters, and go to logarithm. So now they're in the same units. So now we can go ahead and complete the final task, which is comparing the 2 data sets, or the strain semantics that we want to compare. So we're going to go back up to the top here and go to CAD FEA, compute deviation to 3D data set. And once again, you want to keep this straight in your mind. You want to make the basic data set the major strain. You want to subtract out the FEA data major strain. It's going to automatically name it, and now you're going to hit OK. Now you'll see that the comparison was actually made. You'll see the green or whatever colors appear on your screen. You'll see the strain semantic difference. You'll see the histogram, and it's all in true strain. You might not work in true strain, but this can be fed back up to the simulation team to say, hey, look, we verified it. This is how it should be used. And you want to repeat this function for the other strain semantics that you are comparing. So now we're going to do this for minor strain as well. So CAD FEA, compute deviation for 3D data set. We're going to make our basic data set the minor strain. We're going to subtract out the FEA minor strain. The name at the bottom automatically updates. We're going to hit OK. You'll notice the comparison is done here again. Everything updates, and we're going to repeat it one more time for the MECE strain. We're going to make the basic data set the MECE strain. We're going to subtract out the FE data MECE strain. The name at the bottom, again, automatically updates, and we're going to hit OK. So all 3 comparisons are now complete, and you'll notice you now have a list of extra strain semantics that you've created. So if we look at this difference from the major strains here, this is why it's important to keep in track of what you're subtracting out when you do that last step, because now when you're looking at this little red point here, this red area, if you do a control click and you want to report this point back to your simulation team and you turn on the label visibility, you'll notice that this particular point says it's a positive 0.079 true strain higher. So that's telling you that your current measurement is that big, or that plus 0.079 larger strain than the simulation is. This might be important for the simulation team to understand that the current part is straining more than the simulation is predicting. So it's really important on how you report that back to your teams. So with that being said, that's been our workflow of doing an FEA comparison in the ARGUS system. Please rewatch the video if you didn't get it the first time. We appreciate you paying attention, and we look forward to seeing you for future videos. Please subscribe to our YouTube channel, and we'll see you soon. Thanks.